Well, good evening, everybody. It's another time with the Roundtable, and today we are joined by George Hnatiuk with another episode. This is episode 23. We've titled it Reference Frames, and do a quick mic check. George, are you there? Hello, George.
Yes, I am here.
Good stuff. Are you all set up? Are you ready to go?
Pretty much, yeah. I'm just got to get my windows up here.
Excellent, no problem.
Make sure I got it.
No problem.
Okay. Well, I am here.
Well, glad to have you. Hot on the heels from last night, because I know it was quite a late one last night. You jumped on after Gleam did his presentation, and you can see that interaction on the Chit Chat show from last night if you missed it. In the meantime, George is going to be doing a presentation on reference frames. Obviously, reference frames are commonly used with understanding Coriolis. But for this particular presentation, are you ready there, George, now?
Yes, I'm ready. Yeah, I'm just going to, at the end of this, I'll get into a very basic concept of Coriolis. I'm not going to go into the more complicated Coriolis effects. We'll just be discussing the very simplest basic one regarding, shooting a bullet or throwing a ball while you're standing on a roundabout. There's many more. I'll point out some of the more complicated aspects of Coriolis, but that's very basic and the one that everybody seems to be touching on the various shows like Jose and Nathan and others. So we'll get into that. But first, in order to adeptly handle Coriolis, we really need to have a good understanding of what reference frames are and some other important concepts. And I'm going to first touch on one of the most important concepts that we need to get across that I've noticed some people when I review these various hangouts, they don't seem to be quite getting this. And so just to check, is my audio and the video coming through okay?
Yep, everything's fine. Everything's ready to go. We're ready for you to start your presentation, and I'll just leave it up to you. I'll go on mute, and the floor will be yours. So take it away, George.
Okay. Well, I promised someone over in the UK I'd shout out to. You all probably know him. Shroomy, if I don't say something to Shroomy, he's liable to hurt himself. He gets very hurt when I don't acknowledge him. So, hi, Shroomy. We're doing okay. Anyway, the first concept that I want to get down is the conservation of momentum. It's basically Newton's third law, where it says that for every action, there's an equal and opposite reaction. That's just another way of stating the conservation of momentum. Momentum, we designate in physics and engineering by the symbol P, and it's just an object's mass times its velocity. And it's related to the energy of motion of the object that we call kinetic energy. Kinetic energy is the energy of motion as opposed to potential energy, which is a static energy where the motion, an object is not in motion. So kinetic energy can be stated as it's 1/2 an object's mass times its velocity squared. And what's interesting about that is that with this equation, we notice that if we double the velocity, if v is increased by a factor of 2, the kinetic energy goes up by a factor of 4. Or if we increase the velocity by a factor of 3, the kinetic energy goes up by a factor of 9. So it's related to the square of the velocity. But if you notice, mv appears in both equations, so we could also write kinetic energy as 1/2 momentum times the object's velocity. They're inexorably tied together, momentum and kinetic energy. Now, an important thing to understand is that nature does not like abrupt changes. Abrupt changes lead to things called shocks, like with an earthquake or something. In most everyday observations, events, motions, temperatures, and things like that, the changes occur smoothly over short intervals of time. There's no jumps, what we call jumps, where we go from one level to another level instantaneously. That does not happen in nature unless you introduce an impulse to really give it a shock to cause it to change abruptly. But we're going to deal with non-impulse type systems. Now, so we say over brief intervals of time that an object's character before and the object's character after within that brief interval of time does not change. So we designate in engineering, in mathematics, a concept, say, if we have a timeline, we're going a long time, this could be, a temperature profile, could be the motion of an object, its velocity, its position change, whatever, it doesn't matter. But as a function of time, say at some instant in time, call it T1, we want to observe what's happening to that object. And we designate the common language we use to designate what's happening around this instant of time to the left or just a bit before that event, we call this T1 minus. And just to the instant after the event, we call it T1 plus. And that's about time T1. So we've got a little bit of instant before and a little bit instant after the event, T1 minus, T1 plus. Now, let's look at momentum. Momentum, remember, there is the conservation law that tells us that momentum does not change instantaneously unless, again, you input some real, an impulse function of energy into it. We're not considering those situations. So a little bit before T1, at T1 minus, we have a momentum, say, called T1 minus, which is the mass of the object at T1 minus times its velocity at T1 minus. And then a little bit to the right, or a little instant afterwards, we have our momentum at T1 plus, which is the mass at T1 plus times the object's velocity at T1 plus. Well, momentum is conserved. That is, P, the momentum at T1 minus, has to equal the momentum of T1 plus going across the time boundary. The momentum is not going to change. Well, what does that mean? Well, if we look, the implications of this is that we are considering our everyday lives in which at any instant in time, 1 second before, 1 second after, my mass, I don't change. Okay, an object's mass remains constant at before and after an interval of time. So we say that the mass at T1 minus equals the mass at T1 plus. A little instant later, the mass isn't going to change. So if we equate our momentums, then we see that the mass at T1 minus times the velocity at T1 minus is equal to the mass at T1 plus times the velocity at T1 plus. Well, if the masses don't change, they can cancel out. That and that are equal. So we end up with V at T1 minus is equal to the velocity of the object at T1 plus. So the implication is that an object's velocity is smooth. At an instant just before the event, the velocity of the object is going to be the same as it was just a little, as it is just a little bit instant later. This goes into that Mother Nature doesn't like abrupt changes, and that is true for our velocities. We're neglecting the fact that there might be an impulse, like you give something a whack with a sledgehammer or something like that at that instant. But we're not considering those cases. Now, what does this mean? Consider the situation where, say, you have say a trailer, could be a powered trailer, moving down the road, and someone is standing on this trailer. The board is kind of wet yet. Get this thing dried off. Okay, so we have a trailer, flatbed trailer, and it's moving down the road with a constant velocity v. Anything moving with a constant velocity, we call it an inertial frame. So we have a frame of reference here that is constant. It's moving at a constant velocity v, and a person is standing on here. Since this person is standing on this trailer, this person is attached to the trailer and also moving at constant velocity v. Now, what happens when that person all of a sudden jumps up? The trailer is moving down the highway or whatever, say 60 miles an hour, and this person now jumps up off the trailer. So he's now airborne, up off the trailer. Now, we know, we just stated, that the velocity of this person cannot change instantaneously. So the instant this person lifts off the trailer is still traveling at velocity v. That does not change. This velocity and momentum of the person before and after he jumps off the trailer in that instant of time does not change. So he is moving along with the trailer with this lateral velocity v. That has to always hold for the conservation of linear momentum. Our momentum, mv, does not change the instant before and after that person jumps off the trailer. Now, what happens? Well, let's look as the trailer moves down the road, say an instant time later, the trail or a little while later, the trailer's sitting over here. Is that okay? I guess I can see that. The trailer's sitting here. It's still moving at constant velocity v. Now, the person has left the trailer, but neglecting air resistance or anything having to do with the air friction, air resistance, pushing on the person, we're neglecting that for the time being. What's going to happen? Well, the horizontal movement of this person never changes. It's always going to move at velocity v without anything else affecting or forces acting horizontally on this person. So a while later, this person, if there was no gravitational forces pulling this person down, at this instant of time over here, this person would still be up traveling with the trailer. He'd be still going at velocity v. That can't change. That momentum can't change. So with nothing to pull that person down, he'd just be floating in space, traveling at the same velocity as the trailer is moving. Now, but because we have gravitational force pulling down on this person, there's something acting in the vertical direction. So what really happens is in time, the person will actually hit the ground. He's being pulled down. This turns out to be a parabolic path. We call it the trajectory, or the path that the person follows. But at any given time, if I were to take some snapshots, let's say of this thing. Let's say our trailer now is moving down the road. The person has jumped up off the trailer. So our trailer's at one instant of time is here. The person has just jumped up off the trailer. Then another instant in time, the trailer's there. Another instant of time, the trailer's there. The trailer's moving at a constant velocity v. Now, if we look at what's happening to the person, let's put this person, say, up on a perch, or let's say there's something on this trailer here that the person has jumped up off of, so he's higher up off the ground. Now, this person will be moving with velocity v the instant he lifts off this pedestal on the trailer. And as he moves and falls, his movement will be like this. So at the very instant the trailer is over here, this person is also going to be there because his horizontal velocity component has not changed. He's going to track in the horizontal direction the same as the trailer. That's a given. And the only thing that would affect that in real life is air friction or air resistance pushing on that person. But we're just assuming for the moment that that is not the a part of the problem here. Now, so the thing is very important. The lateral velocity, or the horizontal component of any object that's sitting on a moving reference frame, a moving inertial reference frame, that is moving at constant velocity, the instant that object detaches itself from that moving platform, it has the same lateral velocity, the same horizontal component of velocity as that platform is moving. The only thing that gravity affects is the vertical component. It does not interact at all with the horizontal component. Very important concept here. Now, suppose we know that distance traveled, let's say the distance x traveled, we know that's just going to be the velocity times time. So velocity times time is the x direction in the horizontal. What affects it in the vertical direction? Well, gravity does, and it turns out that the equation is that the y component goes as minus g t squared, where g is little g, 9.8 meters per second squared. That anything you drop, its distance traveled in the vertical direction with time goes as time squared. So if you drop something, say, from some height, in the first second, it will go that far, say in 1 second. In 2 seconds, it will go twice as far, or 4 times as far, because it goes as 2 squared. So it'll go down to here in the second second. And in the third second, it'll go 9 times as far. So it'll go way down here in the third second. That's how things drop. That's the consequence of the 9.8 per meter second 9.8 meters per second squared. Now, if we solve for t in the horizontal equation, t equals x over v, and put it in here, we get minus g, then t squared is x over v squared, or minus g over v squared x squared. Well, what is this? Y equals minus some constant k x squared. That in xy coordinates is the equation of a parabola. That's why everything in free flight follows the trajectory or the path of a parabola. Like the water shooting out of your garden hose. If you hold your garden hose up and shoot the water out, that water will follow a parabolic path. You throw a ball in the air, it will follow a parabolic path. Anything in what we call ballistic motion or free motion will always on the earth, over the surface of the earth, follow a parabolic path or a parabolic trajectory. So what happens then is that equation that we just had, y equals minus kx squared, if you were to plot it on xy coordinates, it would look something like this. We would start out, we could start out at some height. We could start out at some height y0, and then it'll just follow this path. And since it's x squared, it's symmetric about, and so what we get is something that looks like exactly like a parabola. Whenever you throw something or anything is in free flight on the earth. So now, so in conclusion, what we've got going here is that the movement of an object leaving a frame moving at a constant velocity, okay? We have an object that's attached to some moving frame and it detaches itself. It leaves this moving frame that's moving at a constant velocity, then that object will have the same velocity as the frame it was attached to. That is the same horizontal component velocity. It will always have that same horizontal component because it has the same momentum. The instant it left that platform, it has the same momentum the instant it leaves the platform as it had when it was attached or standing on the platform, for example. And this is assuming that we neglect air resistance and the object would just continue to move forever in the horizontal component of motion equal to the velocity of the platform that it was on. Now let's talk a little bit about reference frames. I want to get that out first because we're going to get to that when dealing with motions on the earth, the spinning earth and all that. Very important concept about the conservation of linear momentum. Now, reference frames. Suppose in some towns are laid out in a grid system. You have like 1st Street East, 2nd Street West, 1st Street North, 7th Street South, things like that. That is a coordinate system, what we call a Cartesian coordinate system. So let's say we have some streets, and we're going to lay them out in a grid pattern. We're going to talk about reference frames and coordinate systems. And let's say over here, I have two towns. Up here, I've got town Ranty. And down here, I've got town George. And somewhere out in the plain, on the surface of the earth, someone is standing. Let's say here. We want to represent where that person is with respect to our coordinate system. A coordinate system or a frame of reference. We have two frames of reference. We've got frame Ranty and we've got frame George. Reference systems or frames of reference are nothing more than coordinate systems attached to some point in space. That's all it is. It doesn't have to be a physical entity. A lot of people have misconceptions that a reference frame somehow has to be attached to physical entities. They don't have to be. All a reference frame is a point where you put an observer to observe an event. It could be anywhere, any place. Where you place the observer. It could be sitting, that observer could be in a moving car, he could be on a bicycle, it could be swimming in the water, or he could be falling from a plane. It doesn't matter what type of situation you have. All a reference frame is a point where you're making observations. One and the same. To say you have a reference frame means you have an observer making an observation. Now, as a consequence, you can have an infinite number of reference frames in any given situation. You could place a observer on the back of an ant, on a blade of grass, at the top of a tree. You can have any number of possibilities in which you can observe events. And each place that you place an observer to observe an event is called a reference frame. Now, we don't necessarily consider all these different reference frames because at any given problem at hand, we might only want to focus on a few reference frames, and only maybe 2, 3 reference frames are needed to analyze the problem at hand. We're only interested in a handful of reference frames, not all this infinite number of possibilities. Now, so we have a person standing over here, and in, say, coordinate system Ranti, here is my origin. We call a reference point on our coordinate system attached to our reference frame. We call that the origin, and we give that designation 0, 0. We have an x-axis and we have a y-axis that goes through the reference point. And over here, I'm going to call this the primed reference frame. And this is in George. And my coordinates here are prime coordinates. I have x primed, y primed. These are not the same coordinate axes as here. They're displaced from one another. So I have to designate them a little bit differently. So I'll call the coordinate here 0 prime, 0 prime. That's the x prime, y prime coordinate here. Now, suppose I want to represent where this person lies in Ranti's reference frame. So what we do is we count on the grid. So to find this, we extend the grid a bit, say in here, in here. So in Ranti's frame of reference, I go over 1, 2, 3, 4. So my x coordinate is 4, and I go down 1, 2, 3. So it's down -3. So in Ranti's frame of reference, he can locate this person at coordinates 4, -3. How about in my reference frame? Well, in my reference frame, this person, if I extend my coordinates, say this way, in my prime coordinates, I locate this person at x equals 1, so that's 1 primed in my prime system, and I go up 1, 2, 3, 4. So it's 4 primed. So we each observe the person here at different spots. With respect to Ranti's coordinates, this person looks like he's if we're saying this is north, this is east, this person is in the southeasterly direction from Ranti's reference point in his coordinate system, or in his frame of reference. But in mine, I locate that person at almost north-northwest. So this person's position hasn't changed anywhere. It's just that how that person is absorbed from either one of us, from Ranti or me, looks different. Ranti thinks this person is in the southwest, the southeast, whereas I think this person is in the northwest. We're observing the same event, the same thing, but we come away with different conclusions. Now, we can relate these things through how our origins are related. If I look at the prime system from the X system, this origin here is 1, 2, 3, and 1, 2, 3, 4, 5, 6, 7. So the X will be X prime plus 3, and the Y will be Y prime minus 7. So if I put in my coordinates, all I have to do is relate the origins to one another to take Ranti's observation or my observation and convert it into Ranti's observation. So for example, in the prime system, if I put 1 primed in for x, see 1 plus 3 gives me 4. That's what Ranti sees for the horizontal. And if I put in 4 in my system, I get 4 minus 7, which is a minus 3 in Ranti's system. So these are called coordinate transformations. And this is what engineers and physicists do all the time, is if you want to relate one observation to another in different coordinate systems, all you have to do is know the coordinate transformations. Okay, so this is a very simple case where we have fixed frames of reference that are fixed. They're not moving with respect to another one. Now, we can do something a little more complicated. We could take my reference system and have it moving at some velocity. Now that complicates it. How will things look? Well, this person to Ranti is still fixed. He still sees that person at 4 minus 3 just sitting there reading a newspaper or something, whereas I see this person moving because my frame now is moving. And as I move past this person, it's looking like this person is, say, the person is starting here, but as I move, this person is going by me with respect to my origin. So it looks like the person is moving from north through the west to the south. So I see the person differently and the behavior of the person differently than Ranti does. Now there's another yet complication, is it can really get complicated if one of the reference systems now rotates with respect to the other. Then it gets, the coordinate transformations get a little more complicated. They involve trigonometric functions to relate one to the other. Just to kind of give you an idea of what's going on there, I'm not going to go through how to develop the transformations. It's fairly easy, but it's beyond what we need to do here. Is, say, Ranti has his frame of reference and his coordinate system sitting here, and I have mine sitting here, but I'm rotating. Damn. It just doesn't dry fast enough. Okay, so Ranti's sitting here, and he's observing some person sitting there, and I'm in my coordinate system sitting here. However, my axes now are rotating in time. These axes are rotating around, so somewhere later instant in time, my x coordinate will actually be here, my y coordinate will be there. This is rotating around. So I observe this person is kind of walking around me. As far as Ranti is concerned, this person's just sitting there. But if I were to make my observation as my frame is rotating, what I'm going to see is in my frame, I'm sitting here and I'm thinking I'm at rest, and this person is actually moving. So I'm sitting here and I'm observing this person going by me and going around me. Whereas Ranti sees him just sitting put. But from my perspective, in my reference frame, it looks like this person is walking around me. So that's what happens with coordinate systems, is when you start ending up with moving coordinate systems with respect to one another or rotating, things can get rather complicated. And the only way for sure to understand what's going on, you really have to put mathematics to it and develop your coordinate transformations and your equations of motion to really analyze what's going on, except in the very simplest case, like a roundabout rotating or whatever. Now, let's just look, say we're on the Earth, and this is the surface of the Earth. And we're going to also look top down. So let's say we've got a bird's eye view of this, and we're looking down. Now, on this Earth, on the surface of the Earth, say we have a vehicle moving in this direction with some velocity v. Somebody over here has got a rifle and shooting a bullet, and it's going out in that direction. Say Ranty is sitting here on a motorbike, and he's going off in this direction. And I'm sitting here with a bicycle, bicycling down in this direction. Now, the question sometimes you hear people say is, well, how many frames of reference are there here? Well, actually, I answered that before. There's an infinite number. It just depends where you want to put your observations. Just because we have moving entities doesn't mean that's the end of the reference frames. I could put an observer over here to watch all of these people, or I could put an observer here. I can put an observer there. I can put an observer in an infinite number of places to observe all these motions. However, when we're solving these problems, sometimes all we need to do is focus on certain frames of reference. Suppose Ranty here wants to know what this bullet looks like from his frame of reference. So in this case, we can just ignore all these other frames of reference. And from Ranty's perspective, this bullet is going in that direction and he's traveling in this direction. So it looks like the velocity of the bullet, or the bullet, is really going fast from his front to his back. But from the bullet's perspective, if you look at the reference frame of the bullet's traveling this way, Ranty's going that way. Ranty looks like he's moving that way very fast from the bullet's perspective. So again, it just depends upon what you're considering, what motions you want to look at, as to what reference frames you're going to focus on. So it's really a nonsense question to look at a system and say, how many reference frames there are? The answer is an infinite number. But a better question to pose is, how many reference frames are of interest in solving this problem? That's the better question to ask. Now, a complicated system in which you might have Coriolis. I'm not going to solve this problem in this particular hangout. I'll be doing videos on this. I'm actually using this as to help me. I'm going to be doing a video on reference frames to complete my series on Coriolis. And so I thank Ranty in letting me do this, because it's helping me kind of get my thoughts together for my own video. And then from the questions that I get, that will help me understand better what people's concerns or confusion points might be. So suppose this is the surface of the Earth, and let's say we have a crane. You know, these cranes on wheels, they have a swinging boom. It can go up and down. The crane can move right to left. So we're looking down, and we have this crane. And this, the operator is sitting in here with his controls, and he can move this boom right or left. And when he moves it, we have circular motion. So we have a rotating reference frame with respect to the operator here. This boom is moving in an arc, so there's a rotating reference frame. It could be moving at some speed omega. Omega is just how many revolutions per second or per minute. That's a number that represents the angular movement of something when it's swinging in an arc. Now, if we look at this profile-wise, here's the Earth, here's our crane, and he has his boom, but it can also move up and down. Remember, this is a bird's eye view. We're seeing how this crane spins around in the horizontal plane, but it can also move in the vertical plane. So we can have two movements here in rotation. We can go left to right with some angular speed omega 1. We can go up and down in the vertical at some omega 2, and then let's say we have some bug crawling on this crane, and this bug is moving along the crane at a constant velocity v. As far as the bug is concerned, he's just moving in a straight line. This is an inertial reference frame for the bug. He's just moving at a constant velocity in a straight line. The bug is not in a rotating frame. The bug is just moving along the boom of this crane in a straight line at a constant velocity. So the question then becomes, we have two rotating frames of reference. We've got the crane. Let's say the crane is, the operator's lifting the boom as he's swinging his tractor around. So not only is the boom going left to right, or say left to right, as it's going left to right, it's also being raised. So it's doing this arc thing through space. So to compute the Coriolis effects and accelerations and forces in that case gets rather complicated, because you have the cross product of two different angular velocities and a linear velocity. So you can see that these things can get rather complicated, and for someone to say that Coriolis, you only have two reference frames, is wrong. That is in the simplest case, where say you have a roundabout spinning around and you shoot a bullet out. Here you have an inertial frame of reference. This bullet is going in a straight line at a constant velocity, while an observer is sitting here on the roundabout going above. You only have one angular velocity, omega, and a inertial. Whereas in this case that I showed you, we have 2 degrees of freedom. We've got horizontal movement, we've got vertical movement, and we can do a rotation in both, and we can have very complicated Coriolis effects. So now let's look at the Earth and Coriolis. You have any question right now, Ranty, before I go on to that?
Not at the moment. No, I'm looking forward to how you're going to apply these reference frames to the Coriolis, though.
All righty. Just give the board a second here to dry off, get my drink. Okay. Now, let's look at the spinning Earth. Or let's first look at the roundabout just a second, and then we'll go over to the Earth. Now, we have a roundabout, say 10 feet in diameter, something typical you'll find on a child's playground, and it's spinning around at some angular momentum or angular velocity omega. This could be in revolutions per minute, revolutions per second, or radians per second. Typically in engineering and physics, we represent omega in terms of radian measure per second. Or you could talk about degrees per second. Radian and degree measures are related by number of radians equals number of degrees divided by 180 times pi. That's how you get between the two. It's just a constant, which works out to about 59 degrees. There's about 59 degrees in 1 radian. Now, so we have our roundabout where it's rotating around, and now say we have Ranty sitting here on the roundabout. He's also spinning around at the same angular velocity. For any point on the roundabout, the omega is the same for constant uniform angular motion. Every point on the roundabout has the same angular speed omega. What changes is the tangential speed as you move out on the roundabout away from the center. Is the person or a point here on the roundabout is moving faster with a tangential velocity than an object closer in moving with its tangential velocity. In this case, the tangential velocity on the rim is greater than the tangential velocity at some point interior between the center point and the rim. The tangential velocity is related to the angular velocity by the tangential velocity is just omega r. So if you know the constant angular measure or angular velocity, how many revolutions per minute, per second, or whatever, and express it in radians per second, multiply by the distance out from the center, this is our r, then that will tell you how large that tangential velocity is at any given point from the center out to the rim on the roundabout. And this is the number you often see quoted by people like on the equator of the Earth, the tangential velocity, the omega on Earth is about 72 microradians per second. And so if you take that number and multiply it by the radial distance from the axis of the Earth, I'll get to that in a little bit, to the point on the surface, then that'll give you the tangential velocity. Well, out at the equator, we know that we're just directly, that this r is exactly the radial dimension of the Earth, or 1/2 its diameter. So at 6,000, for r of the Earth, at 6,371 kilometers, it turns out, I'm mixing units here. Oh, okay. Thank you. Let's see. Okay. The angular velocity of the Earth is around 72 microradians per second. That's 72 times 10 to the minus 6, or 72 millionths of a radian per second. That's the angular velocity of the Earth. And the way you get that is the omega of the Earth is just 2 pi divided by sidereal period, 1 day sidereal period, which is 86,146 seconds, I think, is what it is. And then that's how you get that number. It's a sidereal period, not a 24-hour period. The sidereal period is short of 24 hours by about 4 minutes. The sidereal period of the Earth, that is the time it takes to make one complete revolution around, is not 24 hours, but it's 23 hours, 56 minutes, and 4 seconds. That's called the sidereal period, and that should work out to 86,146 seconds. Now, so at the equator, if I were to take the radius of the Earth is 6,371 kilometers. If I express that in meters and multiply 72 microradians, the tangential velocity you'll get in English units is 1,035 miles per hour. That is the tangential velocity at the equator. Now, if we were to say, find the tangential velocity for someone in London, they would be at a latitude of about, what, 55 degrees, I believe, in the UK. And so the tangential velocity will be less. It'll probably be somewhere maybe about 700 miles per hour, somewhere in there. We'll get to that in a bit. But the important thing to know is that as you move out from the center, your tangential velocity increases linearly with a radius, is Vt is omega r. This remains constant for everybody, or every point on the Earth or on a roundabout. The omega never changes. Everybody rotates on this rigid body at the same rate. The only thing that changes is the tangential velocity, and that is dependent linearly by how far you are out from the center. Now, let's look at what happens when Ranty shoots his rifle on this roundabout. Okay. Still wet. Okay, Ranty is sitting on this roundabout. It is rotating with some angular velocity omega. And say Ranty is standing here with his rifle. And he shoots the rifle, and the projectile of the rifle shoots out. At that point, that is where it would go if the roundabout wasn't moving. Let's just say for a moment here that we have a stationary roundabout. Okay, we haven't let it start spinning yet. So if Ranty's sitting there and shooting his gun, that bullet's going to go out in a straight line in what we call ballistic motion, free motion. Nothing's going to interact with this bullet other than the force of gravity, but we're going to neglect that for the moment. Now, we start the roundabout spinning with some angular velocity omega. Now, Ranty is sitting here. He's shooting his bullet. Now, the thing to keep in mind is Ranty is off from the center, so he's also moving around with angular velocity omega. And there's a tangential velocity associated with this because remember, the tangential velocity is omega r. He is a distance r out. This could maybe be, say, 3 feet out from the center or whatever. And so there's going to be a tangential velocity associated with that. Well, the instant before that bullet leaves, and this is why I was getting about conservation of momentum and velocities before and after an event occurs in instants of time. That applies to here. The instant before that bullet leaves the muzzle, it is traveling at the same tangential velocity as Ranty is at that point. He's moving. This tangential velocity is like a linear velocity component to the motion. If you look at Ranty sitting here and he has a tangential velocity, if he's over here in another instant of time, the tangential velocity is going that way. And if he's standing, if the roundabout comes about, his tangential velocity is going that way. That tangential velocity gets added to the bullet. The bullet doesn't all of a sudden scrub off and ignore that tangential velocity. The instant that bullet leaves the muzzle, it still has this same tangential velocity component. It has the same momentum the instant after it leaves the muzzle as it did when it was just about to exit the muzzle of that gun. And that's important because what is happening here, if we look at this, Ranty's sitting here. He's shot the gun. He shot the bullet. Now, the bullet is not going to travel along this same line that it did when the roundabout wasn't moving, because there's a tangential velocity component to the bullet. It has the muzzle velocity, call it Vm, going out the muzzle, but there's also a tangential component to it, which causes the bullet to actually move in a straight line a little bit to the left. The bullet will actually be going in this direction because in addition to the muzzle velocity, it has this little tangential velocity component due to the spinning roundabout. So the bullet's going to go in a straight line a little bit off from where he aimed because of that tangential velocity component. Now, what does Ranty see? Well, Ranty's spinning around. Now, as Ranty is spinning around, at another instant in time, Ranty's here, Another instant he's here, another instant he's here. Let's call this T1, T2, T3. Where is the bullet during these instants of time? Say the bullet at T1 is sitting here, bullet at T2 is over here, bullet at T3 is here. These are, say, same incremental differences in time. We're looking at 1 second, 2 seconds, 3 seconds, let's say. So the bullet is going with some linear velocity v. So 1 second it's sitting here, 2 seconds it's twice as far, 3 seconds it's 3 times as far. But what does Ranty see? Well, Ranty now is sitting here on the roundabout. And let's just kind of look from Ranty's perspective, what the heck's going on? Okay, Ranty's starting here at t equals 0. At t equals 2, or t equals 1 there, t equals 2, t equals 3. He's there. Where is the bullet? Well, the bullet is moving outward in this direction in a straight line. So from Ranty's perspective, initially the bullet is right by him. The bullet's getting here. He sees the bullet moving away from him to the right. And then when he gets over here, it's even further to the right. So if we're looking down at Ranty, he sees the bullet hooking off to the right. He's sitting here, and the bullet, he's getting further and further away. The bullet is getting further and further away from him to the right. So he sees it hooking to the right from his perspective, even though the bullet is going in a straight line. So that's the simple Coriolis on a roundabout, is that bullet really isn't curving, but from Ranty's perspective, in his frame of reference, it looks like it's hooking and curving and going along a curved path, when actuality for someone standing here outside the roundabout on the Earth, he just sees it going off in a straight line. This is what we call the Coriolis effect. Now, let's look at the Earth and how that applies. Okay, we've got our Earth, and we have the axis of the Earth that goes through the center of the Earth. Here's the equator, and the Earth is spinning with some omega. That omega, I told you, was about 72 microradians per second. Now, when we look at tangential velocities, we have to look at the component of this vector, or that distance we call r. Here is the radius of the Earth. I'll call it big RE. Big RE is 6371 kilometers. And this is our latitude angle. Our latitude, this is the latitude. Latitudes are measured from the equator. 0 latitude, theta L equals 0 at the equator. Theta L equals 90 degrees at the pole, at the North Pole, and minus 90 degrees at the South Pole. Now, R and RE are related through theta. What we have is a right triangle. It's kind of sloppy. Let's just look at our little diagram here. We have got this box. Here's our RE, and we're looking at R. Well, this is also R right here. And here's our theta L. These are related through trig functions that R over RE is defined to be the cosine of theta L. So to get R, this component, R is just the radius of the Earth times the cosine of your latitude angle. So at the equator, theta is 0. Theta L is 0. Well, the cosine of 0 is 1. So the radial length out is the radius of the Earth. Whereas you go up, say, to let's say we get up to Glasgow, where theta L, the latitude angle of Glasgow is 55.8642 degrees north. And if you put 55.86 into cosine, then your R becomes, what you have is 6371 kilometers. That's your RE. You multiply by the cosine of 55.86, and this number, yeah. Okay. So R, the little r here, will be 6371 kilometers. That's the radius of the Earth. That's the RE. And we multiply by the cosine of 55 degrees, or 55.86 degrees. And this number comes out to 3,571.1 kilometers. So this is less than the radius of the Earth. But that's the number that's important for determining the tangential velocity. The tangential velocity that someone in Glasgow is going to see is going to be this number times the omega. This is going to be omega r, and this would work. This works out to 0.2607 kilometers per second, which is 938.5 kilometers per hour, or 583.3 miles per hour. So you see it's different. The tangential velocity for someone at Glasgow is almost half of what it is for someone at the equator, because remember, at the equator, the tangential velocity is 1,035 miles per hour. So as you get closer and closer to the pole, your tangential component of velocity gets less and less. And that's what gives rise to the Coriolis effect on the Earth, is because these tangential velocities change with position. We'll look at that. I'll show you that. Let's say we're going to do a bird's eye view. We're going to look down on the Earth from the North Pole. The North Pole is going to be in the center, and we're going to look down on the Earth out towards the equator. So here we are at the North Pole. Here's our Earth. This is the equator. Now, here's our North Pole. Now again, remember, the tangential velocity is the angular rotational velocity times the distance out from the center. And that is the r that is defined going to the axis, not the radius of the Earth. This is our r. And again, that's related to your latitude angle. R is the radius of the Earth times the cosine of your latitude. And again, the radius of the Earth is 6,371 kilometers, or in English units, let's see, it's 3,959 miles. Just want to make sure I'm not, okay, I'm still on there. All right, so that's the radius of the Earth. Now, what's going on with the Coriolis? Let's say we're going to shoot southward towards the equator. We're at some point on the Earth. Say we're sitting here. Now, we're going to shoot a gun or throw a ball or something. Let's just do a gun. Say we have a naval 15-inch gun. We can shoot out 20 miles or whatever. And we're going to shoot towards the equator. We're going to shoot due south. What's going to happen? Well, remember, the Earth is rotating with an angular velocity omega which is about 72 microradians per second. Every point on the Earth is rotating with that same number in angular measure. Now, there's a tangential velocity at that muzzle that's determined by, say, this radius R1. Now, we're going to shoot it out. What's going to happen? Well, this bullet is going to be in ballistic flight. It's actually going to be skewed because of that tangential velocity. Remember, this is where it would shoot out if the Earth was not moving, but it's actually going to be a little bit off to the left because of this tangential velocity. So it's going to be going off, but it's still going to be going in a straight line. It's just not going to be lined up with the barrel of the gun.
George?
So it's going off, yeah?
You know you're doing this right now about the bullet, which I'm absolutely looking forward to seeing how you're going to do this with the bullet. But once you've done it with the bullet, is it possible you could do it also with the plane as well? So you can do two different things?
I've got a plane one, a jet that's going to be going.
Perfect, thank you.
The bullet is just easier to handle at the moment. Now, so the bullet's moving out, and as it's moving south towards the equator, all points on the Earth, as we move out from this point, their tangential velocities are growing. We've got a tangential velocity of that magnitude, and that magnitude. The tangential velocity, the Earth is going by faster and faster underneath that bullet as that bullet travels south towards the equator, because these tangential velocities, again, are related through this. As we get further and further away from the pole, R is increasing, so the tangential velocity is increasing. So these tangential velocities, if you're sitting on that bullet and that bullet's traveling out from the muzzle of that gun and heading south, you're seeing the Earth spin underneath you faster and faster and faster as you move south. So from Ranty's point of view, this looks like it's hooking to the right, because in another instant of time, Ranty's over here, the bullet is still there. Another instant, Ranty's here, the bullet's here. So the bullet's getting further and further away from Ranty to the right. So it looks like it's hooking to the right. Well, how much it hooks depends on the velocity difference between when that bullet left the muzzle. The bullet left the muzzle with some tangential velocity, and it travels with that tangential velocity because of what I told you earlier, conservation of linear momentum. That the instant before the bullet left the muzzle to the instant when it, before it left the muzzle to the instant when it exited the gun muzzle, it still has this tangential velocity. That's the important point here. It never loses that tangential velocity. It has this tangential velocity when it's inside the gun barrel. It's rigidly fixed to the Earth, but the instant it leaves that gun barrel, it still has that tangential velocity. That's the important point. And a lot of people seem to miss, is that tangential velocity cannot change from the instant from when that bullet is inside the muzzle to when it leaves. It still has that tangential velocity. So as the bullet's traveling down, the incremental difference in tangential velocities, the bullet is not traveling with respect to the Earth at, say, when it reaches the equator, it's not traveling at 1,035 miles per hour with respect to the Earth. It's traveling at 1,035 miles an hour less the tangential velocity it had when it left the muzzle of the gun. And that is what causes these deflections. The deflection in Coriolis is that if you look at this, let's draw a little bigger diagram. We've got, say that's the equator. Ranty's sitting here with his gun. And our center of rotation is back here. He shoots this bullet. There's a little bit of tangential velocity at this point because he's not right on the pole. The tangential velocity is omega r. this r length from the center of rotation to where the gun muzzle is. Now, when the bullet is traveling, the earth is moving underneath. So let's say we have a target sitting on the earth here. Now the bullet's got some time of flight. Let's call it time of flight, TF. And it also has a muzzle velocity called VM. Now, if we have some distance to our target, call it D, this is our distance to target, then what's important is the time it takes to reach the target and the speed at which it's traveling to the target. Because, again, look at this, is what's happening. The bullet has left the muzzle. It's got some tangential velocity component. It's translating. It's skewing sideways. It has a lateral motion, but as it's moving down in this direction towards the equator, the surface of the earth is speeding up. So by the time it gets to this point, say the tangential velocity at target, this is greater than this. So what happens is during this flight time, if we take our flight time, if we take the differences in the velocities, the difference of time at the target minus the difference of time, difference of the tangential velocity at the muzzle, and multiply it by the flight time, that is the amount of deflection, apparent deflection that you're going to get, called delta X. This is going to be your delta X. The amount of apparent deflection, if Rampy was aiming at this target, line of sight, and he shot, he would miss the target because the earth, where the target was, remember, the target is fixed to the earth, and the target is moving along with the earth. So at the end of the flight time, the target's here, but his bullet was aimed to hit there. It's going to miss the target by this amount of delta X, which is the difference in the tangential velocities from when it left the muzzle to the tangential velocity of the target multiplied by the flight time. That's your delta X. That's why they have to lead for large artillery shells, like in the Navy and stuff. They have to lead the target in order to hit the target. So by the time that shell hits 20 miles later, it's going to hit the target, because if they aimed it just at the target, they'll miss it by that amount delta X, because the target is moving underneath the bullet as the bullet is traveling. See, the bullet leaves the gun, the target's here, the bullet's traveling, the target's moving, the bullet arrives here, but the target's over here. And that's Coriolis. And that's what happens.
Okay, could you also demonstrate that, please, using a plane as well?
Yeah. Let's say you're at Glasgow, and directly beneath Glasgow.
George, could I just interrupt for just 1 second?
Yeah.
Is it possible you could do it on that same diagram that you've just done with the bullet, as opposed to what you're going to be writing here?
Okay.
Just so that we're not getting confused by the two things. I like a like for like, really.
Okay, got it. Okay, here's our center of rotation. Here's the Earth's equator. You're sitting here. You have your gun muzzle, or your gun. You shoot. This is line of sight, say, to the target. But because it has a tangential velocity, the tangential velocity of the muzzle, this bullet is actually going to travel kind of like in this line, because of this tangential velocity. And as the Earth is rotating, The bullet is traveling in a straight line independent of the rotating Earth. It's just going in a straight line. So say at an instant in time, the bullet is there. Well, you've moved to there. The bullet's got here. You've moved to there. The bullet's got here. You've moved to there. And by the time you expect it to hit the target, you're not here, but this is how the target is moving. Here, the target's sitting here. The bullet's traveling at one instant time here. Now the target is moved there. Instant time, the target is now moved there. Instant time, the target's there. Now, by the time it got to where you wanted to hit the target's actually there. So you've missed the target. Now, for an airplane or a jet, the same thing happens. The difference is when we're dealing with projectiles like bullets and balls, there's an important thing called the aerodynamic profile. The aerodynamic profile, and what that is the surface area of the object to its weight. The larger the surface area you have to an object's weight, the larger the aerodynamic profile. And what that does is this is like the principle of a kite. A kite has a large surface area. It can be affected by the atmosphere of the Earth more than, say, a little steel ball. However, that aside, if all of a sudden a plane is flying, and if he, say, is aimed, he has a heading aimed at that target the instant he left your airport here, Ranty, he's going to miss it. He also has Coriolis subjected to him. That hasn't changed. The bullet, the plane, has Coriolis subjected to it. But the difference is that the plane is in powered flight, it has control surfaces, and the pilot can correct for that. And the amount of correction is very, very slight. I have some numbers to show you that. Suppose you're flying, you're up in the air, you've just lifted off, you're here, you have this tangential component, and you're sighting the target. Well, what are you going to do as the pilot? Suppose you see a large tower 100 miles away, very, very, very tall tower, or a mountain peak. You're going to keep your heading. You make these adjustments. You're just aiming your plane to that mountain as you're flying, but subconsciously, or you don't even realize you're making the corrections because you're aiming to the mountain that is moving all the time. And those corrections are very, very slight. I went through some of the numbers, and on a trip that's 380 miles, 610 kilometers, say going from Glasgow down to Plymouth at the southern coast of England, you're in a straight line. They're almost directly on the same line of longitude. And say your speed of your jet is 528 miles an hour or 610 kilometers. Now, I went through the numbers to see how much deflection there is during the flight time and the difference in velocity during that flight. The flight will take, when you're traveling at 583 miles per hour, your time of flight, let's see, where did I put that? Where the heck? Must be on the other paper here. Excuse me a second here. I thought. RP delta T. Oh yeah, the time of flight to go. Okay, let's just put the numbers down. From Glasgow to Plymouth, you're going from 55.86 degrees north to 50.375 degrees north. So your change in latitude is 5.49 degrees. That's your change in latitude going from Glasgow to Plymouth. Your jet speed, let's say the speed of the jet is 528 miles per hour or 610 kilometers per hour. Now, the change in, we're heading down this way. The change in our tangential velocities from when you left Glasgow to what the tangential velocity is of that target, that tangential velocity change between those two is 128.2 kilometers per hour, or in terms of seconds, it's 35.6 meters per second. That's the change in the tangential velocity. We're making a trip. The length of the trip is 600. The trip distance, call it D, is 617. What's that? Gosh, it's 617 kilometers, okay? That's the total trip. And it's taking the time for the trip is 215 or 2,615 seconds. Now, what that does for you is over that time, you're looking at about 3/4 of an hour flight time, a little over 45 minutes. Now, to correct for Coriolis, all the pilot has to do is change his heading by 8 degrees over that flight time. And what that works out to is that for every 10 seconds of flight, he would only need to make a correction of 0.033 degrees. The resolution of the human eye is 0.02 degrees. And for every 10 seconds of flight, the pilot would only need to correct 0.33 degrees, just a little bit more than what you can even perceive a change in 10 seconds. Where in a minute, it works out to 5 times this, or 6 times this, which would be on the order of 0.2 degrees per minute. That's all you have to correct for. It's very, very slight. So for every minute of flight, when you're flying about 530 miles an hour, going from Glasgow to Plymouth, you only need to correct that flight, that plane's heading, 0.2 degrees, 0.2 of a degree every minute. Very, very slight. You wouldn't even notice it if you're just aimed at this mountain that happens to be moving. You wouldn't even know that you're making that correction. That's how slight these Coriolis things are. They're very, very slight. So it's no wonder why, a lot of pilots don't realize that they're correcting for Coriolis, because it's a very, very slight correction that you need to make to stay on the proper heading to get to where you're going to arrive.
Okay, George, just one last thing, because I know that you've just done a north to south there. Would it be possible if you got rid of the equations and just put the Earth back up with the centre and do an east to west flight and a west to east flight, if that would be okay, and give us the times that it would take to travel those distances?
Okay. Oh. Okay, what we just had was this, where we were moving. This is too wet. Okay, let's say we're going north to south, and we started off here, and the corrections that we needed to make, we found are very, very slight. The target is going to be over here with the plane, and like I said, the amount of correction that you need to make to get there is on the order of 0.2 degrees for every minute. Very, very slight. Now, let's look at, we're going to go top down. We're looking from the North Pole to the equator. Let's say we're on the equator. And say we're going to fly, the Earth rotates in a counterclockwise direction. Now let's say we're going to fly in this direction. Now, this is where a lot of people get buggered up. And Brian Mullen did this. Again, remember, conservation of momentum. The instant the plane leaves off the surface of the Earth, it has the same tangential velocity as the surface of the Earth. It does not scrub that off. It does not lose it. It still has it. So, at the equator, the tangential velocity is 1,035 miles per hour. The plane is here. It's taxiing down its runway. It lifts off. Say with respect to the runway, let's just say for purposes of argument, the plane has reached 300 miles per hour on the runway. It's sitting on the runway. It just lifts off at 300 miles per hour. Okay? With respect to the surface of the Earth. But the surface of the Earth is traveling at 1,035 miles an hour west to east. The plane has that velocity. The instant it leaves the runway, it hasn't lost that velocity. That's still there. That's the tangential velocity. The plane was sitting on the Earth. The Earth is moving in this direction. The plane is sitting on the Earth. It has a velocity of 1,035 miles per hour. It just lifts off the runway. It still has that component of velocity, but going in this direction, with respect to the Earth, it's only going 300 miles an hour. People like to add and subtract this from the plane, and that's wrong, because the plane, the instant it leaves the runway, it has that same tangential velocity component as it had when it was sitting there, just with its wheels running down the runway. It has this same component of velocity. It never loses that. So the instant it runs off the runway, it has this velocity with respect to the surface of the Earth, and it's moving this way at 300 miles an hour. The Earth is rotating in this direction. So actually, with respect to someone in space and at the center of the Earth, the plane, with respect to someone out here, looks like it's traveling 1,035 miles an hour in this direction, less 300, so about 700 miles an hour in this direction. That's the plane's velocity with respect to somebody out in space. Well, what's happening to this city it's trying to get to out here? Well, this is traveling also in this direction at 1,035 miles an hour. Well, the plane is also going in that direction at 700 miles an hour. So, how the difference between these two is about the 300 miles an hour that it's going to fly along the surface of the Earth to get to that destination. Nothing's changed. People are just incorrectly accounting for the spin of the Earth or the tangential velocity of the Earth when they do these things. Nothing has changed. The important thing to keep in mind is the instant the plane leaves the surface of the Earth, it has the same component, the tangential velocity component, as the Earth did the instant it lifted off. So nothing has changed. The plane travels with respect to any point on the Earth at 300 miles per hour. Cities don't come to it sooner, or going in the other directions, the cities don't recede any further. It's just the velocities with respect to the surface of the Earth, because you're forgetting to add that tangential velocity component that the plane had when it was sitting on the runway in the instant it left it off. That tangential component of velocity does not disappear.
So just to be clear then, there's no perceived difference in flight times when you go east to west. Is that? Hang on, I've got you on mute. So there's no time differences when you fly east to west or west to east, so you don't really have any effect of the Coriolis. But if you travel from north to south, you do have to take into account Coriolis.
A little bit, not much. Like I said, it's ever so slight, because the plane is traveling, a typical flight, a plane travels so much slower than a bullet. A bullet goes, a high-speed rifle bullet's 2,500 feet per second. That's about 5 to 6 times faster than a jet flying at 500 miles per hour. So the thing is with a bullet, it can get from its point of initiation to its target a lot quicker. So there's a deflection there that is the bullet can't correct for, because it's in ballistic flight, it's in free flight. Whereas with a pilot sitting in a plane, he's sitting there with his coffee, his drink, his Dr. Pepper, like me, or whatever. He has plenty of time to make these corrections, and the corrections are ever so slight. Like I said, for a jet traveling at 530 miles an hour between Glasgow and Plymouth on the southern coast of England, that's around 46 minutes of flight time, and he only has to correct 0.2 of a degree every minute. That's basically negligible. How much? Look on a compass, draw out someplace on a piece of paper and see if you can really discern 0.2 of a degree. It's very hard. It's very, very slight. You have a circle, there's 360 degrees. 1 degree on this circle is probably about like that difference. And we're talking 1/5 of that over a minute. Very, very slight. It's very hard to discern that angular difference, let alone 1/5 of that angular difference in 1 minute of flight. You have many more problems with wind shear and headwinds and tailwinds and crosswinds and stuff that affect the flight other than Coriolis. Coriolis is ever so slight to correct for when you're in an aircraft, because again, remember, you're lifting off with the same tangential velocity that the runway had at the instant you left off. There's conservation of momentum. You can't deny that. It has to be continuous. Your velocity, the instant your wheels were touching the runway to the fraction of a second they left the runway, you still have that tangential velocity component. And so that's why you don't have these cities receding from you or coming to you faster in an east-west versus a west-east direction. That's because you have neglected the fact that the tangential component of the Earth's spin stays with the aircraft the instant it leaves the runway or leaves the Earth.
Okay, so back in World War II, when they used to fly from Great Britain to bomb the Germans in Berlin, etc., and they used to fly at night, so they used to fly the bombers, etc. So they just had a heading to go to. How were they able to get there if they had Coriolis moving underneath them, which they would have needed to accounted for had they had line of sight? But if they were flying at night time, how were they able to actually get to Germany and drop those bombs at the locations? Because by your account, they would have traveled.
I'm sure they had navigational equipment. I'm not exactly sure what they had on board of these bombers, but even in World War II, they had gyro compasses and things like that to help them do their navigation. They weren't just doing, they were flying by instruments. They weren't doing line of sight at nighttime. They were flying by instruments. Okay. Gyro compasses, gyroscopes. They had even in World War II, they had some fairly sophisticated navigation systems. It was more mechanical than we have now. A lot of our stuff is more electrical, like ring laser gyros and things like that, but they had mechanical gyros. In fact, most light craft these days still have mechanical gyros. They have them in boxes, these Honeywell ones. They're in boxes about yay long, and they're square like that, and they fit inside the console. And I've seen one of these. I went down to Wentworth Aviation in Minneapolis. I was looking at getting one of these, but they're enclosed. You can't really see what's going on there. All they have is some electrical connections that come out. I wanted to kind of put a window in it to use that mechanical gyro to do some tests, but it turns out you can't. They're in an evacuated atmosphere. They pump down the chamber that these mechanical gyros on these very precision gimbals are. They pump it down to about, he told me, 4 to 5 psi is what these are operating in. And, back in World War II, they did have these precision gyros and navigation systems. So, it's not out of the question that they were able to navigate at nighttime. I don't see why that would be a problem, because they had instruments. They flew by instruments.
Okay, so we have a super chat from Nathan Oakley, George's ace. We have a question from John W, who says, can George explain how a V1 bomb would hit its target over 100 miles within a 2-mile radius? Note, the V1 did have a basic gyro to help keep the plane level.
How what? No, how a V1 or a what, B-52 bomber, what? No?
A V1 bomb, so I'm assuming that's a bomber, would hit its target over 100 miles within a 2-mile radius. Note, the V1 did have a basic gyro to help keep the plane level, but no gyro, nothing other than that.
I don't know. I can't speak to the... I can't really intelligently answer that, because I'm not a expert and not familiar with World War II navigational systems and what they may or may not have had on board these planes.
Okay, but if it can be proved that the planes in World War II didn't have the most sophisticated devices to actually get them to hit the target, and they actually just they just flew in a heading rather than following the actual instruments.
Well, I'm sure there was more to it than just headings. I don't know if you've ever flown with private pilots or not. I have many friends here in northern Minnesota that have their own private planes, and I'm very good friends with the owner of Inertial Flying Services here out of International Falls, and I fly a lot with these people, and they fly by landmarks, not only the instruments help them, but a lot of time, you're up a mile or whatever, you can see out 90 miles when you're a mile up.
Yeah, sorry, just to confirm, the V1 was an unmanned bomb, actually, so it wasn't a bomber. So a V1 bomb was an unmanned bomb. They just basically line of sighted it, and it hit its target.
Well, I'm saying I'm not the person to be answering that question. I'd have to research that. I'm not going to offer an answer on that, because I might say something wrong.
Okay, fair enough. There was a question right at the very, very start by LBB Store. So, given an aeroplane's takeoff speed is slower than its cruising speed, is an aeroplane flying west on the equator slower than the spin of the Earth at takeoff, effectively flying backwards?
No. Because you still have the tangential component of velocity as the surface of the Earth, and you just speed up relative to that or slow down according to going from takeoff speed up to cruising speed. You haven't lost that tangential velocity. You're just adding or subtracting to it as you change your airspeed.
Okay. In answer to your question about have I flown planes before, yes, I have. I've flown bulldogs, chipmunks, gliders. So when I was in the Air Training Corps, I was pretty good at flying. I enjoyed it. Pete Shea asks, ask him, is a heading fixed or does it depend on speed?
I'm not an expert on air navigation. I know I've talked to many pilots, and I know one of my good friends just retired from Delta Airlines, and he was flying the 787s, these big jumbo jets. And I asked him about the navigation systems on there, and he said they're all electronics. All he does is push buttons. He says he doesn't have to know anything about any of this, which rather surprised me. He said all he does is punch in the heading, punch in the altitude, and away it goes. And the plane through its jet through its control surfaces maintains altitude, maintains the heading that apparently the computer inside makes the corrections. What you do is you punch in the code for the airport that you're headed to. Like here, I'm in INF, standing for International Falls. That gets punched in. The computers know all the coordinates of where these things are, and it makes the necessary corrections by reading the GPSs and stuff, and the pilot just sits there. He's only there for emergencies. The plane, today's modern jets take care of everything. It rather surprised me. I mean, he even told me that the artificial horizon that you have on these, he says he never uses those things. The only time a pilot uses these artificial horizons on these commercial airlines, he says, is to watch when you are doing a bank or a turn to maintain your bank within a certain angle to keep the passengers comfortable. He says you just want to make sure that you're not banking too steep, and that's the only time he ever uses it.
Okay. So, listen, I have a personal question to ask you on this. It's probably one of the first ones I've ever asked on these shows, but I haven't seen the actual question that I'm looking for in chat, so I think it's needing to be asked. How long does the tangential force of the plane when it lifts off? How long does the plane keep its tangential force?
Well, without an atmosphere, a tangential velocity, you mean, without an atmosphere, it'd be indefinitely with nothing, with no air friction or anything. So with air friction, of course, it's going to affect it, but that's easily corrected for by applying power or pulling back on power on the jet. I mean, again, these corrections are easily made. I mean, these changes occur over a length of time. They don't occur all of a sudden instantaneously, where you're talking about dipping the nose or something to maintain over the Earth. This is another point. I've heard this so much.
So to keep its tangential velocity, if it's losing some of that due to the atmosphere, does that mean that a plane flying west to east and a flying plane east to west, one of them's going to use more fuels than the other?
No. Again, the tangent going east-west, you're not changing anything. Your tangential velocity is maintained. Once you lift off, It's just all airspeed corrections or whatever. I mean, you're going to have more problems with headwinds or tailwinds and stuff like that than you would ever with these. There's no change in tangential velocity as you're going direct east-west. That never changes. It only changes when you're going north-south as you're moving away or towards a pole. That's the only time your tangential velocity changes.
Okay, and the tangential velocity, why does the plane maintain a tangential velocity? What's that? What keeps it travelling at that speed?
Well, there's a number of things. Again, it's momentum. The thing, I guess I didn't get that through clear enough, is if you have something moving, say this trailer, and you're on the trailer, and you're moving at a velocity v, and all of a sudden you jump up off the trailer, you're detached from the trailer, you will have that velocity v forever. If it weren't for the fact that gravity was pulling you down and you end up crashing to the earth, or there was air resistance, you'd have that velocity v forever. That's a conservation of momentum. The momentum you started with is the momentum you're going to maintain forever. That's Newton's first law. What does Newton's first law tell us? That an object at rest will tend to stay at rest unless acted by an outside force, or an object in motion will tend to remain in motion in a straight line at that same velocity forever until acted upon by an outside force. That's Newton's first law. You will have that velocity forever, that tangential velocity forever, if it weren't for air friction or air resistance or anything like that. So you make up for the air resistance, the viscosity tending to slow you down by just applying a little more power to the plane. But you maintain that tangential velocity forever.
Okay, so that brings me back to my original question, which was, would those two planes that I mentioned, one flying east to west and one flying west to east, surely if they're encountering wind resistance or atmosphere, there should be one using
yeah,
more...
of course, that's going to affect your flight time, sure.
Okay, so at what point would the atmosphere get rid of all the tangential velocity?
Well, probably if you had 1,000-mile-an-hour wind,
okay.
Which doesn't happen.
Okay, right. So I'll ask a couple of questions if I can find any in the chat, and let's see. Just having a quick look up to see if I can see anything right now. I think there was, but I can't find any right now. Right, you're going to be back. You're going to be hanging on the line, I'm sure, because we're going to do a chit-chat show soon.
Yeah, I'll stay here for as long as anyone wants me.
Okay, so I know that we're going to get Pete Shea. He's going to come in, and I'm sure that a couple of other people want to join too, so we can just have a chit-chat. I don't want it to be heated. I'd rather just have a civil conversation. So if anybody's got anything to say about this particular subject, by all means, bring it up. George, thank you for coming along and doing these presentations. I do appreciate it, and I appreciate you taking your time out to come here. Right, give me 20 minutes, people. I will be back at 12:10 with a chit-chat show, so don't forget to tune back in. And yeah, as for now, this will be the end of this particular segment. This is 23, Roundtable 23, reference frames with George Hnatiuk. And this will do for now, and I'll see you all.
Hey, Randy, stay on Skype a minute. I want to talk to you a sec.
Sure. And we'll see you all in the next one.
As soon as you go offline.